title of this presentation is Functional Program for the Object-Oriented, but I have a little small disclaimer here, and that it's going to be more about functional programming than object-oriented. But I want to first ask the question, why am I here? I have probably a quite unusual background in software development, as the first job I had coming out of university was doing full-time programming in a functional language called Haskell. How many of you have ever done anything in a functional language before? So a couple of you, about a third or something? All right. How many of you have done work in an object-oriented language? That's almost everybody, right? That's pretty dominating technology you'll be working with when you're doing programming. But I started off working with Haskell and doing functional programming. And then after that, I had a job where I started working with C++. So I got to work with object-oriented languages instead and learn about that and what there are the effects of doing that in a real-world environment. Of course, I learned about object-oriented language in school and stuff, but actually using them in the real world is different, as you all know. You learn a lot from doing that. Then I got a job at Click, and there I started working with C# instead. How many of you have worked with C# before? Okay, so about half of you, all right? So when I started working with C#, I got thrilled because I noticed that in C# you have a lot of constructs that very much map to things I've learned about functional programming. And I got to use a lot of the things I've learned and that I valued in functional programming in C#. And I also noticed that my colleagues were sort of thinking that the way I wrote my code was sort of strange. Yeah, someone are laughing here, but and they started calling me Mr. Lambda and stuff. I used all these Lambda expressions and all this link layer stuff. And after a while, I sort of figured out that perhaps it would be good for me to actually explain why I'm doing this and give a little of my background. So this presentation actually came out of that. So I want to talk a little about functional languages and how they map to C# in particular, but other languages as well. And I hope you'll find it interesting. So first of all, let me start by looking a little at programming paradigms. Everybody know what a programming paradigm is? Sort of? All right. So I took a look at Wikipedia when I started building this presentation. So I'll just read this up. So a programming paradigm, according to Wikipedia, is a fundamental style of computer programming serving as a way of building the structure and elements of computer programs. Okay, very open and nice. Then I looked at imperative programming. And imperative programming is a programming paradigm that describes computation in terms of statements that change a program's states. So statements that change state. Now if we move to object-oriented programming, the definition looks like this. So it's a programming paradigm based on the concept of objects. I'm sure you're all very familiar with that, which are the data structures that contain data and code in the form of procedures, often known as methods. And then for functional languages, or functional programming, it reads like this. It's a programming paradigm that treats computation as the evaluation of mathematical functions and avoids changing state and mutable data. That's sort of cryptic, but it's very different from the previous ones. Actually applying this to a specific line of code is sort of difficult. But I saw a presentation once for a couple of years ago. It's still on the internet. I can really recommend this for those who are interested. By a guy named Daniel Spiewak. I'm not sure where he's from, but this presentation is good. And he gives a presentation where he talks about some of the what happens sort of in the borderline between object-oriented and functional languages. And he takes a very pragmatic approach to this whole paradigm thing. And he says like this. So an object-oriented programming, objects are the things you use as a primary unit of abstraction. And for functional programming, he would say that functions is the primary unit of abstraction. An interesting thing here, I think, is that what you see, this has nothing really to do with languages. It has to do with how you model your problems. What are the tools you reach for when you want to solve some problem? And he continues and says this. So in a functional programming, functions are the primary tools you reach for when you want to model a problem. All right. So what does that imply then? Well, let's have a small case study here, a very simple one. This is about the for loop. I'll show you all our written for loops at some point. So this is the first version where I'm using what I call direct indexing here. This is written in C. How many have written a for loop like this lately? Using an index? Yeah, a couple of you, okay. So we have this one. This is what I encountered when I started doing C++ programming, using an iterator structure. How many have written one of these lately? What languages are you using then? You over there, which language is that? C? Okay. Then we have this one, using a for each structure. How many? Almost all of you. Yeah? This has started to be sort of dominating, right? You eliminate another complexity by doing this. And also a very nice thing about this is that it hides all of these unnecessary references to specific elements. This expresses much more tightly what you actually want to do. I want to do this for each element of this set. Then we have this one. How many have written one of these lately? Actually, quite a few of you. Okay. Nice. So what's so special about this one? Well, I would classify them like this. Perhaps that's not so big surprise now. So this, I would say, is the imperative way. This is just statements operating on state. Here, I would call this the object-oriented way, because here, the tool I reach for is an object. It's a class. It's the iterator class. That's what I reach for to solve this problem. And this one here is the functional way, according to the definition we heard. Because here I'm just reaching for this function. I'm doing a write line, and I'm writing all my customer names using this function, the for each function. I'm just applying this write line function. Someone who doesn't agree on that?
Change the state of you mutate the state.
Sure. So I'll go back to that, but obviously you will never write a program that doesn't change any state. But I would say that to solve this, functions are the tools I reach for. All right. So that's it about this introduction. So I will split this this presentation into two, as you heard, and we will have pizza in between. In the first part, I will give you a sort of a very quick crash course into Haskell. So I will show you many of the structures that are in Haskell and how to apply them. And I will also try to compare them to what I see in C# in particular, but object-oriented language in general, to see what are the influences from Haskell, because you do see a lot of influences from functional languages these days. And then the second part, I will sort of try to leverage what I've gone through here and show you how to solve a non-trivial problem by using Haskell, functional programming paradigm. All right. Any questions before I start? Excellent. So here we go. Introduction to Haskell. Of course, if you want to see a new language, the first thing you need to see is the hello world, right? So here we go. Hello world of Haskell. It looks like this. It's very straightforward. It's just a put line and then the string. This is actually an executable program. You can compile this and run it. You will get this nice hello world string right in the console. If I want to do input, I can do something like this. So I will write, hi, what's your name? And I will do getLine to get that value, and I will just print that out, hello, ++. And this is the concatenation operation for joining strings in Haskell. If I want to do some form of branching, I can do like this. So I can add an if statement. So if the name equals Barack Obama, I will write, hi there, Mr. President. Otherwise, I'll write your name. Okay, so this is written in Haskell, which is very much a functional-oriented language. But I would definitely not say that these are functional implementations. I would say that these are strictly imperative implementations, actually. And one thing to see here is that, again, the style of programming you do is not really tightly connected to the language you use, or at least it doesn't have to be. Just like you can code in an object-oriented style in C, that doesn't make it an object-oriented language. And you can code it imperatively in C++ without any problem, or in C#, or in Haskell for that case. So what's so special about Haskell then? Well, I'm going to start from the bottom. So the first thing I'm going to go through is some basic types in Haskell and how to write them, just to get the annotation straight. So obviously you have some primitives. So you have booleans, characters, float, int. Integer is a sort of special type in Haskell. It represents an integer value that doesn't have a max or min. So it sort of abstracts away the size. The only thing that limits it is the size of your memory in your machine, basically. Then you have lists. Lists are used a lot in Haskell, and they are written like this. You have these square brackets around them. So this is a list of int. This is a list of characters, which is actually the same as a string. So this is so short for writing like this. So if you write a string ABC, that's actually this string of 3 characters. Functions are written like this. So you have type annotation like this. So this is not is the logical negation. It takes a boolean and returns a boolean. And this is the logical and, which takes two booleans and returns a boolean. Then we have tuples. How many here use tuples regularly? Sort of a third or a quarter, yeah. So this is the type of structure that you'll find in most languages these days, but they're probably not used as much. In Haskell and in functional language in general, I think you will use them a lot. It's a very useful thing, especially when you need to return multiple values. You need them, basically. So this is the way to, if you want to have a type that is two-dimensional point, you can have two integers like this. Three-dimensional point with three, or you can mix different types. So if you want an address, you can do something like this. You would have a name, a street number, etc. All right. Pattern matching. This is a concept that is used a lot in Haskell. And this is usually used for pattern matching on input values into a function. So if I want to implement a logical AND operation, I can do something like this. So my AND takes two booleans, and then I pattern match on the different values I can get here. I'm constructing sort of a truth table here, right? So this will sort of map into some sort of case statement that you will see, but I'm doing this on the different arguments. So my AND true equals true, my AND true false equals false, and so on. Of course, this doesn't scale very well if you have a lot of different values here. So instead, you can use wildcards. So you can write this like this instead. So my AND, where I have a value false first, always returns false. I don't care about the second value if I know that the first is false. So I can just return false. And if I have true in the first value, then I can just capture the value here in some variable x, and I can return that, because that will be the result of it. Pattern matching on lists is the next step here. So let's say we want to write a very simple function that just summarizes all the elements of a list. It will have this signature. It takes a list of integers and returns an int. And in Haskell, you will often use recursion for doing this type of behavior. So we will start by some form of base case. And the base case would be the empty list. It usually is when you're working with lists. So sum of ints of the empty list is 0, right? Nothing strange about that. And the sum of a non-empty list that can be pattern matched like this. So this represents a list that has at least one element. And we sort of pattern match the values to these different variables. So this n here will be the first element of the list, and ns will represent the rest of the list. So then I can do like this. I will add n, and then I will recurse on that to say sum int on tail of the list. If I want to count the numbers instead of adding them, I can write something like this. So it's exactly the same thing. The only thing is that I'm doing a wildcard and a value. I don't care what the value is. I'm just returning 1, right? So an interesting thing about this now is that I actually don't need this value at all. I don't care what the elements of this list are. And that brings us into a domain where Haskell uses something called polymorphism. So you can express a function like this. You can express a function length that takes a list of a, and a here represents a type variable. The fact that it's lowercase here is important in Haskell. Uppercase values represent data structures, data types. Lowercase represents type variables. So length here takes a list of any type. It doesn't care what the elements are, and returns an int. And the definition of the function will be identical. It doesn't really matter. Make sense? Okay. So polymorphism. This is a pretty important concept in Haskell because it allows you or makes it possible for you to construct these very nice general functions that can be applied on any types. So it's a way of sort of generalizing a behavior into a function that you can apply in many different domains. And perhaps the simplest function you can write that is polymorphic is the identity function. This is a type of function you probably don't see much outside of the functional world, so to speak. But this identity function is a function that takes a value and just returns it. So what do you need that function for will be the first question. When on earth would you do that? But I will come back to this quite a lot because it's actually pretty useful when you start working in a functional style. And Haskell provides a lot of these polymorphic functions that works on any types. So here are some of the functions you will find on lists. So the length, as we already saw, this is predefined, so you can just use them out of the box. Concat takes a list of lists, merges them into one. Head and tail returns the first element of the list. Tail returns the all but the first elements of the list. This is indexing in the list. So if you want to have the third element, you can do a list exclamation, exclamation 3. Take and drop will drop a number or take a certain number from a list. And zip will take two lists of any types and merge them into one list of tuples. So it will pair up the different elements of the list. And then when one of the lists gets to the end, it will just drop the rest from the other. So if I have 4 elements in this and 5 elements in this, then this will result in a list that is 4 elements long. Next concept I'm going to talk about is higher order functions. So when we were looking at implementing these two functions, the sumInt and the countInt, we can see that they actually have quite a lot in common. Actually, the only difference here is what we do with this value here. In this case, we return it. In this case, we just turn it into 1. So now we can, instead of writing like this, we could write a higher order function for this. So we will write a function that takes a function as argument and this list and performs this operation and applies this function that we give it on the values of the list. So we could write it like this now. FoldInt takes a function from int to int and this list of int and returns an int. Base case will be the same. And in this case, we have this f here, which is the function we want to apply. We apply that to the first element. And then we just do recursion here. See, I missed the f there. F should be in there. Any questions on that? Pretty straightforward, right? OK. So now, what if we want to do... So now we can actually write like this. So we can use all of them. You had a question? So now we can use this function here that we wrote here to do a lot of different things. So we can define sumInts with it. We will pass the identity function. Right? We just want to keep that value. Or we can turn it into 1. This is a lambda expression in Haskell. So we have this slash here and an argument. We don't care what the argument is. We always want to return 1. Or if we want to do, we could do the sum of squares by passing in a function like this. Just multiply the number by itself. All right. So what if we want to... Was there a question? No? What if we want to do this on strings now instead? Imagine that you want to write a function like this, concatenate. That takes a list of strings and returns one string where we have just merged them all into one. That would be implemented something like this. So the base case would be the empty list again, and we will return the empty string. In the recursive case, we would again pattern match with a list of one element, and take that element and do concatenation with that, and what we get when we do the concatenation of the rest of the list. Now, if we compare this to the implementation we did for sumInts, we can see that they're very, very similar. So we can start to list what are the sort of common attributes of these two functions. Well, the first one is that there is a base case. Up here, it's the empty list. Here, it's 0. All right? Next thing is that there is a list of values. We're doing this operation on a list of values. And the third thing is that there is a function that takes two values and combines them into one. So why don't we write a new function, a higher order function, that sort of captures these aspects instead? Let's call it a fold. Anybody heard of fold before? Some of you? All right. You might understand where this is going then. So a fold takes a function, it takes two values, and it takes a base case, and it takes a list of values, and returns the result of what you get when you use this function over and over again to fold the list. And when we implement this, it will look something like this. So for the base case, we have the empty list. We don't care about the function in this case. We just return the base case. That will translate to this run of this. And for the recursive case, we will just take this function here that we get and apply that to the first element of the list and what we get when we fold the rest of the list. Now we can use this for a lot of different nice stuff. For instance, we can implement concatenate like this. Concatenate on a list of strings is just a folding where we use this concatenation operator, give it the base case like this, and apply that to the rest of the list. Or we can implement a lot of different functions. If we want to summarize the elements of a list, we could do like this. We fold with the plus operation, and the base case is 0. If we want to multiply all the elements, we provide the multiplication operator, and the base case will be 1. If we do 0 there, we won't get much interesting results, right? Or we can do for different types like this. So if we want to do AND on a full list, a function that returns true if all the elements of the list is true, we will give the AND operator, and the base case should be true. And for OR, it should be false. So what have we actually done here? Well, the way I see it, fold is a function that captures a quite common way of operating on sets of values. We have sort of abstracted out how to navigate our way through doing an operation on all these values. It's a generalization of a type of iteration that you will be doing all the time. And this makes fold one of the functions that is in your toolbox when you're working in a functional programming style. And Haskell will provide you a lot of these different functions. Fold is one of them. And here are some aspects of these polymorphic higher order functions. It's a very neat name, but that's what they call it. And actually, we'll find that most of those iterative patterns that you want to do on sets of values are already captured in some form of predefined function. For instance, you have map. This is probably the most common version that just applies a function to all the values of a list. You have concat map that does sort of the same thing. It just returns a list here. So we'll return a list of all for each value in the first list and just merge them into one. So it's a combination of map and concat, basically. Filter returns all the values from a list that satisfies a specific predicate. So all elements that return true for this function will be returned. Take while will return values as long as a certain predicate is true. All and any will just apply a predicate and say that if all of these values satisfy this function, then you're all okay. Zip with is a version of zip that you saw earlier that takes two lists and combines them into one tuple. This takes a function, it takes two values, A and B, and returns C, and applies that pairwise on the elements from two lists. And the result is a list of type C. And again, if one of these lists gets to the end, then it will stop. So the length of this will always be identical to the length of the shortest of these two. Iterate is sort of an interesting function. I'll come back to this a lot later. But what this basically does, it takes a function from A to A, so it has to be the same type here, and a starting value. And then it creates a list where it just applies this function over and over again. So if I provide the value, a function +1 here, and I have a value 0, I will get the list 0, 1, 2, 3, 4, and so on, forever. And then we have a fold functions that we've already seen. Actually, in Haskell, you have two different of them, fold R and fold L. That sort of folds from the different sides of the list. It has some very specific cases where that will be important. You can also see the actual type here is a little more general, and if you look more closely at it, you will realize that it's possible to define them like this instead. In the version I had, we all had only one type all over the place, but you can actually lift those restrictions a little. Now, this set of functions is a very powerful set of functions. There's a lot of things you can do with them. And this is sort of where the object-oriented world comes in. Because when I came to Click and started working in C#, I quickly discovered the link library. And the link library is basically an effort to try to bring all of these concepts into C#. And the link library provides actually most of those methods or functions that I just showed you are actually provided there. So the map function in Haskell translates to something called select in C#. And everything here works on a specific interface called Enumerable. Enumerable that has a certain parameterizable value. So if I want to double the values of all elements of a set of values in Enumerable, I can use the select here and provide that function. Select many is the same as concat map that you saw here. Filter, translate directly. Take while, all, any. Zip with is actually just called zip in C#. The zip that creates a tuple is not there. But of course, you can provide a function that creates a tuple if you want to. And the fold L in particular, is expressed as aggregate in C# in Link. I couldn't find a version of fold R there that folds from the right. Perhaps it's in there, I don't know, or perhaps you can modify that in some way, but it's in there. Yes, but one important thing here is the fact that if you want to use this, you will be using functions as arguments quite a lot. You don't want to define those functions from scratch, writing a big set of code that, int function returns, blah, blah, blah. So when you do this, lambda expression starts to become very important because you want to have a lightweight way of creating your functions. That's where lambdas come in and why they are important. I know in Java has been very hesitant to introduce that, but it has been introduced lately, I believe. It's not that long ago, but it's available now. But a language that doesn't support lambda expressions will have a very hard time writing a library that does this in a convenient way. And convenient is important there, because if it's not convenient, you probably won't use it. Java has a similar library like this. And this was introduced in SEA 2014, is that right? I don't know how many of you have been using that. So I think this is very new in Java, actually. But there you have a library called Stream, a standard library called Stream, that gives you many of these functions as well. So you can see many of them translate here. So you have a map function that takes this stream, and you can apply that function to all elements. Flat map is same as select many. Filter, I couldn't find a take while in that library, but I'm sure you can construct it if you want to. All match, any match, zip with I couldn't find. Again, you should probably be able to construct there. Reduce is the name of the fold function in Java, in this library. And Java also has this iterate function. Again, I'll talk a lot more about that, but that's not present in C# out of the box. I know there are some other libraries available for Java as well, something called functional Java, that I think probably captures more of this. So I've never looked at that, but that could be of interest if someone wants to look more at Java there. So, next concept I'm going to talk about from Haskell is the concept of lazy evaluation. So lazy evaluation is something that allows the program to just compute stuff on demand and just only exactly what it needs. So imagine that you have some very expensive method, say ordo and faculty here. It could be like traveling salesperson or something, right? Something that is really heavy. And I can add that to a list. So say I have this list here when I have expensive 1. So this will take like 2 days to compute. And here we have value 2, a constant. And I index it with 1. Then actually running this will be very, very quick. Because I will never have to compute that value. It's never returned. It's never actually affecting anything. So the language will just drop it. It doesn't care what it is. And the same thing if I do a length on the list where I've applied this to all the elements. So I map expensive here on my int list. This will still be very quick, just ordo n. Just take the length of the list. However, once I start using it, and it's actually supposed to have some effect, then I will run into trouble. So if I write a function like this, so here I assign expensive 1 to a value, n, a variable. I show it, meaning that I want to create a string from that value. I get that to s. This is all very quick, but when I do this, string line, that's when I hit the performance issue. Because at that point, I'm actually going to do something with that value and write it to the console. So at that point, Haskell is going to start truing. This can give some surprising effects sometimes in where things start to slow down when you're working with Haskell. But it can also be very, very beneficial. And it has some other applications as well, apart from the pure performance thing. And that is this concept, infinite data structures. So what is an infinite data structure? Well, it's a data structure that has no end, basically. And this iterate function that I showed you earlier constructs exactly that for you. So when I do iterate, I give it a function, Here I give a function that adds 1 to the value. And I start off with 0. Then I get a list like this. 0 is the first one. Then I apply the function once. I apply it twice, 3 times, 4 times, and so on indefinitely. And this will never stop. And so why would you want to do this? Well, often you won't need the entire list. It could be that you just need the first 10 elements. And that's okay, because since this is lazy, it will never have to compute those values that are behind that. So we'll just give you the first 10, and it will be done. However, if you try to compute the length of this list, then you'll be in trouble. Or if you try to get the last element of it, that won't give you much. So how can we use this then? Well, another thing, in Haskell we have some nice syntactic sugar for this, because you use this actually quite a lot. So if you want to create this list, you can just type like this, square bracket 0, dot, dot. That will give you that infinite list. So here's a use case for you. Something that I've actually done from time to time. So let's say you have, you want to create a string that is a numbered list. And I do that from a list of strings. So here I have a list containing this is my list, and I want to create this. 0, 1, 2, 3, and there's the text strings. I could write that in Haskell. I'll show you how to write that in Haskell now. First of all, let me just implement a function that writes one of these rows first. So print entry will take a string and an int, and it will write one of these. It will basically look like this, very straightforward. I just show the value, turn this into a string, I add the colon, and then I print the string. Now I want to use this in the function that actually creates the numbered list. And this is a function that takes a set of strings, a list of strings, and returns one string, the long string that I print here. And it can be implemented like this. So what am I doing here? Well, first of all, I'm using the zipWidth function. Remember zipWidth? It takes a function that combines the values of 2 lists into one using this function. The last argument here is a set of strings. First argument, or this argument, is the infinite list starting from 0. A nice thing about this is that this will be the limiting factor. We know that this will have a finite number of values, but I don't have to care about how many they are when I compute this one. I can just keep counting, and it will just solve itself by itself. And then I use this function here that I already defined to combine those values into one. So this will give me a list of strings where I have combined these for all of them. Then I just join them with this sort of nice utility function. Unlines takes a list of strings and return them with the new line character at the end. Lazy evaluation in C#. Actually, some of these aspects are available there as well, and I believe also in Java. I have very little experience in Java, but I believe the Stream library can do this for you as well. So C# has introduced something called deferred execution. I think this was introduced already in 2005, so it's quite a long time ago. But what they've done there is sort of interesting. They have introduced this yield keyword that has the effect that it returns a value, and then it passes control back to the function that called it. And once that function that called it actually wants to access one of those values, it will continue and produce the next one. So it will produce them on demand. It's very useful. I think this was originally designed for simplifying access to databases and things like that. It's actually a very, very nice feature. So let's see how we can implement this iterate function in C#. In Haskell, it could look something like this. So iterate takes a function and a value, and always returns the value. Then iterate by applying this function to the value once and doing this recursively. This is now a recursive function without a base case. It's going to just run forever because we will never stop there. In C#, it could look something like this. So the iterate function takes a value parameter here, a type parameter, t, and a function from t to t, and a value t. This is sort of exactly analogous to this. Then we just do an infinite loop. And we return the x, which is the value we have right now, and then we just continue by setting the x to the f of x and just doing this forever and ever. So this will result in an infinite stream of values of this type. So let's do a quick example where I actually utilize this. So when I go to a new programming language, I want to do some very simple project just to sort of get my hands dirty or something. And one thing I would usually do is that I want to write a function that generates primes. Okay, I'm sure you already have all done that at some point in your education or something. So Sieves of Aristophanes, however you pronounce that, is an ancient algorithm for generating all primes. And it works like this. You start off with a set of all integers greater than or equal to 2. Okay, so an infinite set of values. Then you return the first number in that list as a prime. 2 is a prime, right? Nothing strange about that. Then you filter all the values you have by removing all the numbers that are multiples of the prime you just removed. So in the first notion here, we will remove all multiples of 2. So we remove 4, 6, 8, and so on. Then we go to 2. So after the first loop here, the value that will be at the head of the list will be 3, because we removed 2. That is a prime. So then remove all multiples of 3. Then the next value that is the head of the list will be 5, and then 7, 11, and so on, right? So let's see how we implement this in Haskell. The type would be that we have a function called primes that is basically just a list of integers. When we start off by passing it this infinite list here, starting from 2. All integers from 2, greater than or equal to 2. Then this Sieves method here can be implemented like this. So it takes a list of ints and returns a list of ints, a filtered set of values. We pattern match. We know that the first element of the list is a prime. So we just return that. And then we filter out all the elements from the rest of the list where the remainder is different from 0 when we divide by this prime. And then we do sieves on that. And then we can just keep chewing like this. It's not a very quick algorithm to find primes, but it works. It's sort of nice, I think. Kind of like the history aspect of it. This can be implemented in C# as well. So we already show you how to implement the iterate function, but we could implement the rest of it in C# like this. So we want to have this function sieves that we want to create, which is actually the interesting part here. And we create the iterate. We use the iterate to create this infinite list, starting from 2. Then we can implement that like this. So we take the enumerables of ints. These are the primes that we get, or prime candidates, I guess. We return the first one. That we do with this yield return here. That is important, because if we don't, this is what allows us to generate this infinite list. It allows the caller to chew this off on demand. And then we just do this filtering here. So this is the exact same filter condition that we did here, up here. So here we just take those values where the remainder and divided by the prime is different from 0. So that will do the same thing. And this will actually work fine in C# and will give you this infinite list concept on primes. All right. I think we soon have the pizza break, but I have 3 concepts I want to go through before we take that break. Then we'll hopefully use this after the break. If not, I'll sleep after the pizza. Let's see. So classes in Haskell. Classes in Haskell is very, very different from classes in an object-oriented language. A class in Haskell refers to a type class, a class of types that has, and a type class provides some certain constraints on what that type could do. So for instance, we have a type constraint on functions that utilize the equality operator. So the type of the equality operation is like this, EQA. This means that the type A can be of any type, but it has to be a member of the type class EQ. And there are types that you can't compare, right? It's very difficult to compare functions, for instance. How do you compare 2 functions? And there are other types that also don't have an obvious equality operation. So you will write it like this. So you could be any type, but it has to be a member of the equality class. And the equality class will contain, will describe something like this. I think there's a little more in here in Haskell, but this is our important thing. So if you have a type that is a member of the equality class, it will provide you with these, it's guaranteed to provide you with these 2 functions, equality and inequality. And these constraints will sort of propagate as you program. So if I want to write a function that checks whether or not a certain element exists in a list, I could write like this. So elem takes a value in the list and returns true if any of the values in this list is equal to this element I'm looking for. Now this definition requires us to use this operator here, which in turn requires us to be part of the equality clause. So this can only be applied to values that are a member of the equality again. So this will sort of propagate out there. I couldn't do this on a list of functions, for instance, because I can't compare functions like that. So examples of usage would be this. If I do lm3, I can do that on a list of integers, 2, 3, 4. Strings are also have a nice equality comparison rate. So I can do, is my an element of this is my list? Yes, it is. I can find that. Another class that you encounter quite often that I will sort of return to later is the enumeration class enum. And this provides a lot of different operations. For instance, you have a from enum that you could, for instance, use to turn a character into its corresponding int in ASCII. Right? It also has this successor and predecessor functions that will return you the next value. So if I do suck on 1, I will get 2. If I do pred on 1, I get 0. Right? And I can sort of traverse those values in the enumeration type using that. So examples of usage for that would be, for instance, like this. I could do map suck on 1, 2, 3. I will get 2, 3, 4. If I do map suck on HAL, I will get IBM. Anyone recognize that? Yeah? Did you know that? No. So anyone know what HAL is? 2001 Space Odyssey? Excellent. I got to put a sort of nerdy film reference here. So this is sort of a conspiracy theory thing that it was actually a sort of a coded word for IBM when they did that movie. I wrote that book. All right. There you go. So, 2 concepts more before the break. Partial application is a very nice concept in Haskell. This is actually probably the functionality that I miss most when I work with C#. This is a very, very useful thing when you're working with higher order functions. So what is partial application? Well, imagine that I want to write a function like this. Double takes an int and returns an int. Very easy to write like this, right? N equals 2 times n. Now, types in Haskell are sort of special. You can actually look on functions as all functions being of a type that just takes one value. So in this case, it looks like it takes 2 values, but actually if you only provided the first value, what you end up with is a new function that takes an int and returns an int. So if I look at the type of this application here, where I provided both of the values, that expression would have the type int. But if I provided just one value, then what I end up with is a function that doubles, because I've already provided one value, but not the second. So I get this new function here. And this is really nice, because it removes a lot of necessary of writing these lambda expressions all the time. You can just provide one of the values. So now I can implement my double function like this. Double is simply 2 times. I don't have to give any reference to this first value here. Yes?
Is that called currying?
No, that's not currying. That's something else. Yeah. Currying is when you turn a function that takes... I never remember which one is curried and which is uncurried. But if you turn this into the other version, you will get one that takes a tuple instead. Yeah. So I think a curried version is the one as a tuple. So it takes a tuple with infinite, or the other way around, I don't remember. So if I want to double all the elements of a list, write a function to do that, I can do like this. So double all takes a list of ints and returns a list of ints. And double all, don't give any argument here. I don't pattern match on anything. I just say that that is the function that maps times 2. And that's it. All right. Last concept, functions on functions. And after this, you will have pizza and a break. So another thing you need when you're working with functional programs is functions that combine functions in different ways. I'll show you some example here. But one of the very typical things you would do is use this function application operator here. So this is a function. First time you see it, it's sort of like looking at the identity function. What on earth will you need that for? But this operator takes a function and a value and applies that function to the value. So again, why would you need that? Can't you just apply the function directly? Well, in some cases, this is very useful. Actually, one of them is very sort of pragmatic, because this is a very low precedence. So you can do like this. You can skip a lot of parentheses by using this. That's probably where you use it the most. So instead of having parentheses around this, I can just say that I want to apply this part on this part. It's just a nice syntax sugar or regularly. But it also has some very specific effects. For instance, in some cases, you want to use this in terms of passing it to a higher order function. So here I have a list of functions. I have a list that contains the successor of function, the predecessor function, and the times 2 function. Now I can map this apply to 2 on all of these. So what will this mean? Well, it will first provide this function here to this one, and here I've provided the second argument. So this will have the result that I'm applying suc to 2, then I'm applying pred to 2, and times 2 to 2. So I will end up with the values 3, 1, 4. Did I lose anyone there? No? Some? Okay. Remember this, because I'll be using it after the break. Function composition. This is also a very nice thing in Haskell, because it's very easy to do. And a function composition is basically what you get when you want to apply 2 functions after each other. So this, it's actually denoted this, just a dot. And it takes 2 functions, one from B to C, one from A to B, and returns a function, basically, that takes an A, input value here, and returns a C, output value here. And then it applies these 2 functions in sequence. So you can implement it like this. G.f is a function that takes an X, first apply F, and then applies G. And it's very useful when you want to do things like this. I want to take all the values that are not even in my list. I can just do filter, even, not. And I combine those 2 into 1. This is also something that is sort of tricky to do in C#, unfortunately. But there's quite a few times I want to do that. And it would do the function is null or empty on strings. I did that today, actually. And I said, why can't I just do a not dot this one? That would be nice. But unfortunately, you can't. All right. Here, actually, I have this curry and non-currying functions as well, because you will find a lot of sort of curious functions here that at first glance looks very, very strange. And one of the ones that I usually sort of joke about when I talk about Haskell is flip. A flip takes a function from A to B and reverses the order of the arguments. So why would you want to use that? Well, in some cases, you need to, because you want to apply a certain function as part of a higher order function, and you need to sort of get the ordering of the arguments right. So sometimes you actually use that. It's not very often, but it's sort of a curious little function. Curry takes a function that takes a pair of values and returns a function that takes 2 values. And uncurrying is the other way around. So it takes a function that takes 2 values and returns a function that takes a pair of values. So it's sort of transforming those functions on the fly. All right, any questions here? No? Nothing? Non-specific ones. Okay, so I've given you a very brief crash course in Haskell now, so I understand if you don't remember all of this. But after the break, I will actually use this to solve a real problem. So hopefully it get a little clearer why I've done all of this and why I've introduced this stuff for you. So, pizza, it's yours. So this part now will concern actually applying what I've shown you here and solve a real problem. And the problem I'm going to solve is this one, the 8 queens problem. How many of you know what that is about? A couple of you. How many of you actually implemented a solution for that in the language? 1? Just 1, okay. 2, all right, nice. This is sort of an exercise. I think perhaps did this in university. At least I've done it a couple of times in different aspects. So the 8 queens problem, what is that all about? Well, The problem is this. You have a chessboard, 8 times 8 squares, and you want to be able to put 8 queens on this board without 2 of them being able to threaten each other. It's actually sort of tricky to do. If you go home and do this afterwards, you'll find that it's not that easy to do. But it's an interesting program exercise to do this. It's sort of non-trivial, but still pretty easy to grasp as a problem. Actually, the reason why I chose this problem in particular was that when I had this job where I was doing C++ coding, I had a colleague that was curious about Haskell and wanted to learn this, and he jumped on this problem. And he sort of asked me, like, how would I do this and how would I do that? And I realized he had a very, very different approach to solving that problem than what I would have had. And if we were to do this in an object-oriented language, if I were to do that, I probably would think of things like, okay, what's the classes I would need here? I'll probably be the chessboard class, right? A chessboard class that perhaps has a method called place queen, or a method called check if queen is okay to place, or something like that. And that was sort of the approach he was doing. And immediately the question popped up, how do you create an 8x8 matrix in Haskell? How do you use arrays in Haskell? And the answer is you don't. You don't use arrays in actual Haskell. Actually, Haskell doesn't have the concept of arrays at all, which is sort of strange when you think about that. But if you think about what an array is actually something that is very closely tied to pointers. Because if you want to have an array and have this constant time lookup thing, you actually need to have the concept of consecutive memory locations. And in Haskell, you don't have that because you don't have pointers. So actually working with arrays in Haskell is not very easy. Of course, you can use lists instead, but you would probably not get the performance you want if you really want to do things in arrays. So the answer is you usually don't. You do the problem in a different way. So how would we do this in Haskell? Here it goes. First of all, the thing I started with was, what would a solution look like? What is actually the output I want from this function that solves this problem? And I was thinking this, hey, the only thing I need actually is a list of rows. I know that I can only have 1 queen in each column, right? So that's easy. So why don't I just have a solution represent which row a queen is in each column? So the solution here, which is actually a real solution, could look like this. 3, column 1, or 7, depending on where you count from. 1, 6, 2, 5, 7, 4, 0. That is the solution to the problem. So, the solution strategy I was looking for is sort of a greedy algorithm where the goal is to create all solutions, all possible solutions to this problem, and just take the first. This is something you can easily do in Haskell because of this laziness, right? I don't actually create all those last solutions. Once I have a solution, it will return it to me. So where do we start? The empty solution. So I will start with some form of base case, a solution where I haven't placed any queens yet. And then I will start adding queens to this empty solution. And we end when we have a solution where there are 8 queens on the board. So what functions will I need to solve this problem? Well, I will need to be able to extend an incomplete solution. I will sort of have intermediary states here where I have a partial solution that I want to extend with a new queen, or see how can I extend these solutions with new queens. And I will need some form of function that checks if it's okay to add a certain queen to a certain row in a certain column. Okay? So let's look at this solution extension. So here we have a partial solution. We have placed a queen in column 0, 1, and 2 at these locations. So we have this partial solution here, 7, 4, 0. Now, what we want to do then is if we want to create the extensions to this, what we can do is just create all of them. Try to create all of these extensions and see which ones are okay, and just throw away those that aren't. So we would do like this. Let's add all the queens. 8 different possible extensions to this one. And then we start chewing off one after the other. So we will check this one. Is this okay to add here at row 0? Well, it's okay to add up here. It doesn't threaten anything there, but it hits this one. So that's not okay, so that's removed. Then we take the next one. Is this one okay to add? Well, it's okay to add up. It's okay to add level in the same row. And it's okay to add down. Great. So that's a possible extension to this one. So that one we keep. Then we take the next one. This one is not okay to add because it will hit this queen. And then we just continue like this and look for all of them. And we end up with actually just 2 possible extensions here, which are these 2. So given this partial solution, we have 2 other partial solutions. We added a new queen to the 4th row, row number 3. So these are the 2 possible extensions, 1, 7, 4, 0, and 5, 7, 4, 0. All right? So let's start looking at this function here that checks whether or not it's okay to add a certain queen at a certain row. So it should have this type signature. It takes an int, which represents the row we are trying to add a queen to, and then it takes the partial solution we have where the queens are placed in the first n columns. And it should give a result like this. So if we do OK to add 0 on this list, it should do false because we're hitting this one. If we try to add 1, it should turn true, as we saw on the previous slide. Now there are 3 different cases here. One where we are looking if we are hitting a queen on the upwards diagonal, one we are looking at the downwards diagonal, and one we are looking at just the same level. So I'm sort of splitting this into 3 here. So now we can define OK to add like this by using these 3 functions. So it's OK to add a queen if it's OK to add it up, and it's OK to add it down, and it's OK to add it level. That's sort of a divide and conquer strategy for approaching this problem here. So let's look at the OK to add level first. This is pretty easy actually, because in this case, what we want to do is just scan our way to the right and see if there is a queen there. And how do we do that? Well, what we want to check is just whether or not this is a part of this list. So we can just write like this. OK to add level takes a queen and a set of queens, a partial solution, and returns true if Q is not an element of QS. Now, if you remember what I said about partial application, there's a very interesting thing here, because actually you can write like this. You don't need any arguments at all, because these 2 are the same function. OK to add level is the same function as checking whether or not something is an element of a list. That sort of simplifies that one. Next, OK to add up. So now we are trying to place this queen here, and we want to traverse upwards like this and see if we hit a queen there. So how do we do that? Well, we start off from position 1 here. So what we want to do is to increment 1 by 1 up to 2, which is this row now. And then we want to check that is 2 the first element of this list. If it is, then we hit a queen here. But if we didn't, it's up there. That's OK. Then we do the next one. We increment again to 3 and check is there a queen in the second element at position 3. No. Then we do 4. Is the last queen in position 4? No, it isn't. So it's green all the way. And then finally we reach the empty list, and then we know we're home safe. There are no more queens to hit. So if we want to write this using recursion, we can do like this. OK to add up takes a queen again, a possible row position to place a queen, and a partial solution, and returns a boolean indicating whether or not it's OK. The base case is this. It's always OK to add a queen to the empty list. We're at the end of the chessboard, so it's OK to add it. The recursive case is a little more complicated. So what am I doing here? Well, for each step here, we want to increment 1 to see if there is a queen on the place that is up to the right from where we are right now. And as we are doing recursion, we sort of traverse this one here and continuously increment 1. So I'm doing this. Here I'm first pattern matching on these queens. So I put a name on the queen I'm trying to add, Q0. And the head of the partial solution I call Q1. And I want to see that if this now will match this one after I move up to the right. So I define this value here. Let Q0 up be equal to the successor of its current position, which will be 1 step up. And then I can just compare these 2. I move up to the right now, so does these 2 match? They have to differ, otherwise I hit a queen. And I want to check if it's OK to add up on what remains of the list. So that will sort of recursively chew off the list of possible queens to hit. All right. Now there's another way to look at this. which I would say is sort of more functional. If you didn't think that was functional, this was going to be. So imagine that we do like this. Let's just create the diagonal set of numbers starting from where we are. We take a list that just creates these ones. So we start from 1 here, so we will get 2, 3, and 4. And what we in reality want to do is to sort of do a pairwise comparison between the values in that diagonal and the partial solution we have. And how did we do a pairwise comparison between lists? Anyone? Zip width. Zip width take a function and 2 lists and does a pairwise operation on those values. So if you use the equality operation there, it will just compare them. Yeah, I can skip this one. But how do they create the diagonal now? Well, we just want to have the numbers incremented by 1 all the time. So we can use iterate. Our queen starts off of 1. So if we want to create a diagonal, we can just iterate successor on 1, and we will get this infinite list that is the diagonal up. Now we want to drop this first element here, because that's our starting position. We are just looking at the queens after us in the row. So we'll need to drop that. We'll get back to that. So that's one way to create a diagonal. And then we have the zip width method. So if we provide this list here, except for the first one, and do a zip width on inequality here with our partial solution, it will start doing this comparison just like we want to. It will do this. Is 2 equal? Does 2 differ from 7? Yes, it does. Does 3 differ from 4? Yes, it does. Does 4 differ from 0? Yes, it does. And then it reaches the end of this list, and then it's done, because we just cut away the rest of this list. So this operation gives us a list of booleans. And we want to check that all of those booleans are true. So we will use these 2 predefined functions as well. First of all, we need tail, that we need to drop this first value here. And then we'll do and, which takes a list of booleans and returns true if all of those elements in that list are true. So now we can define our function like this instead. So OK to add up. We're just anding what we get when we zip this diagonal with our partial solution. And we iterate up from the queen that we are trying to place. All right? So now let's look at OK to add down. This is actually very similar. Anyone want to give it a try? It's this. It's almost identical. The only difference is the function we're using here. And immediately when you see that the only difference is the function, you want to create a higher order function, right? Of course, why wouldn't you? So then you get something like this. We want to create a function that we call OK to add given dir, or direction. Takes an int, which is a possible queen position, and a partial solution, and a function that denotes how to create this diagonal. Is it up or is it down? Returns a bool. And the implementation will be identical. The only difference is if we take this f here, we pass that in there. So now we can write these functions as this instead. So OK to add up, that's OK to add given there with suck, and OK to add given pred on down. And by the way, how about OK to add level? This can also be written like this. You have a suggestion? Identity function, exactly. So if we apply the identity function, we will just scan to the right. So we can write like this. So now we can go back to our original function, which was the sum of these 3 functions, which was OK to add, which took these 3 cases. If we rewrite this now using the functions we just had, it will look like this instead. So we apply this function to these 3 functions over here and just add them together. Can anyone guess what my next step will be here? We are applying this function to 3 different values. Why don't we just create this list? So extract those functions into a list. suc, pred, and identity. And then we can use this function, a predicate, function all, that takes a predicate, that takes a value, a function from a value to a bool, and a list of values, and returns a bool. Now our list of values here will be functions. And this function here will be a function that takes a function, namely an int to an int. So now we can define it like this. So OK to add takes a queen and a partial solution, and returns true if it's OK to add given there on this one for all of these functions. All right, so now we have the OK to add. That returns true if it's returns whether or not it's OK to add a certain queen to a certain partial solution. So what's the next step? Well, just a summary of where we are so far. We have two functions. We have the OK to add given there, that we saw, this one, and we have the OK to add. So now we want to do some extension. We want to use these functions, or actually want to use the OK to add function in order to be able to create extensions on solutions that we already have. So the idea here is now to take one partial solution and find all possible ways to extend that solution with one queen. So we want a function with which has this signature. It takes a solution, and it creates a list of solutions, which are all the extensions. So how do we define this? Well, there are 8 possible queens that could be added, one for each row. And that you can write like this, 0 through 7. This will create that list 0, 1, 2, 3, 4, 5, 6, 7. Then we want to filter out the ones that are OK to add. All the rest can be discarded. We have a partial solution here. We want to just take those values that are OK to add. This is a neat way in Haskell to write all functions as infix, by the way. So this will now become the second argument, sort of syntactic sugar. It's pretty nice. So in our initial solution there now, or the partial solution we saw, with doing this will give us 1 and 5, I believe, right? Those are the two numbers that are OK to add. Then we want to take those numbers that we get and create lists that contains the partial solution we already had and adds that value to the head. That you can do like this. So what am I doing now? Well, this part is the same as there. What I added was this part. I'm mapping this function. And this function now takes a value and adds that to the head of the list. And I'm mapping that to all the possible extensions that I found here. And there we go. That's the function. So extend solution looks like this. Maps cons QS on what I get when I filter out the ones that are OK to add. So now we soon get into the end of this. So the next step now is that we have this function that extends a solution, or creates all extensions of a solution, and we want to apply this consecutively until we have added 8 queens. We want to apply it 8 times to all the solutions that we get. So step 1, we will start up the empty list, and if we apply extend solution to the empty list, we will get this. It's exactly what we get. Because it's OK to add a queen to all rows in the first column when we start. Then we want to take this solution and apply extend solution to all of the elements. So we want to apply extend solutions to this value, which just gives us these possible extensions. We cannot add a queen to row 0, 1, because they will threaten the queen in row 0, in column 0. But we can add number 2, and every combination above 2 with 0. And then for the next solution here, we know we can't add 0, 1, or 2, because all those will threaten the queen that we already place, but the rest of them are OK, and so on. So we get a list of lists, actually. A list of containing all the possible solutions for all the possible extensions. And we would just want to merge all of them, because all of these are candidates for becoming sort of the solution we are actually searching for. So we take all of these and just join them together into one. Then we just repeat, and repeat until we're done. So now that you have this one, we want to do the exact same thing. We want to map extend solutions on all of these, join them into one. Map extensions on the result of all of those, and join them into one again until we're done it 8 times. So how do we implement this then? Well, so here's a signature that I'll be working with right now. It is called all solutions. It takes a number, which is the number of times I want to do this extension. And it returns a list of all the solutions that are available when I've done that many types of extension, performed extension that many times. The base case is very simple. If I want to extend 0 times, I should get exactly one solution, and that is the empty list. So how many different ways can I place 0 queens on a board? Well, there's exactly one way, and that is the one where I haven't placed any queens. And then the recursive case, here I want to create all solutions that have n-1 queens first, and then I want to extend all of them and merge them into one. So I can do like this. Creating all solutions with n-1 queens is easy. Just do like this. All solutions n-1. That's the recursion, right? Then I map extend solutions on that. You had a question? No, okay. I map extend solutions on that. And then I just merge them into one. And the function to do that is concat. Or I can use this concat map, which is just a shorthand for that. This is something you do quite often, so we have a special function for that. That is predefined. So this will do the trick. Concat map, extend solutions, all solutions, n-1. So the full version will look like this. And what we're going to do with this is to provide it number 8. Because we want to apply this 8 times to get to a solution where we have 8 queens. However, if you look at this, you can see that we're actually doing something here that sort of follows another pattern. Because if you see multiple apply function n times, you should think iterate. I'm actually iterating here. I'm applying the same function over and over again. And what is the function I'm applying here? I'm applying the function concat map extend solution. So I could instead express this using iterate, like this. Because this will capture exactly what I'm doing. It's starting from a base case, and it just applies this consecutively over and over again. It creates a list where the first element will be this value. The second element will be all the possible solutions where I added 1 queen. Second element will be all the possible solutions where I've added 2 queens, and so on. And then I can just take number 8, or number n that I'm looking for. So I can just do indexing like this. Double exclamation and n. And as I am providing 8 to this one, I will get all the solutions there are for 8 queens. So the final version will look like this. All solutions take the value n, which is the number of queens, and I just iterate this function and take number n. Then the final part here is just to wrap it all up. So now I have a function that creates all possible solutions for a certain number of queens, and I just want to create all possible solutions for 8 queens, and then take the first. And it looks like this. So this is the top-level function, right? So a solution is a list of integers, and the solution is what I get when I take the first value I get when I create all solutions with 8 queens. And that's it. And this slide shows it all. This is the entire implementation of everything. How many are surprised to see how short it is? Yeah. It is short, and actually I myself was sort of surprised when I saw where this was going when I was implementing the first. And I think that's a very interesting observation to make, because why is it so short? Well, I always say it's so short because I'm actually not doing much implementation. I'm just reusing functions that are already there. I'm just using the toolkit that is there to do the work for me. And back to the question that you had, Jakob, where I can't read this. Because I would say most of you probably, if you get this solution, you would say, huh? And that was the first reaction. I gave this presentation to colleagues of my clique as well, and that was the first reaction. I can't read that. And yeah, I take your point, but on the other hand, I think that when you start using these functions and you get used to them, you have them as part of your everyday workflow or everyday toolkit, you sort of get familiar with all these functions. I'll show you what it looks like. So I have an implementation here. Let's see where to go. So here it is. Emacs, for those who are using that. And I can bring it up here. Let me launch this one. So I'm running a Haskell interpreter here that allows you to not compile this, but actually run it interactively with this. So now I can just run this function that I had, solutions. Let's see. There you go. That's a solution. And if I want to look at all the solutions, I did a slight modification to what I showed in the presentation, if you can see that. I removed the argument to this one and moved that over here instead. So this doesn't need that anymore. This will just be an infinite list. This list allows me to do something like this, for instance. I can do all solutions and do this indexing 8. These will be all the solutions there are of length 8. I can ask how many are there? There are 92. So I would leave it for exercise for you if you go back home and look at this to see how many of these are actually unique, because you get a lot of mirroring stuff in there. What's that?
No, so it was fast for being brute force.
Yeah, it's just 8 queens. So if you move it up level, I actually tried that. What happens if you do 10 and then you start feeling it? If you do 12, it goes really slow. So this is sort of exponential in how much time it takes. But I can also do something like this, which is sort of interesting. I can do map, length, and then I take the first 10 versions here. I will get the number of solutions I get for a number of different queens. You can see it has sort of a nice function here. If anyone you are savvy in mathematics, you can probably sort of calculate an expression for that one. And I can also do something like this now to simplify reading perhaps. If I do zip this with 2, or I will get this. So I'm enumerating them. So I can see which one is the most. Well, it's this one, where I've added 5 queens. That's the top, and then it starts shrinking. And for 9 queens, there are 0 solutions. And all solution after that will be 0, of course. All right. So that's basically it. So what's my point here? Can anyone try to guess? My point, if I go back to where I started, was that when I came and started working with C#, I started using this link layer quite a lot. And I was using these functions that you see here. Zip with, you would see filters, you would see maps. And these were sort of a natural part of my toolkit. And I found that very valuable when working in C#. I probably wouldn't have written a queen solution like this in C#, because there are some tricks here that makes that difficult. But there are a lot of things to learn that I think is valuable for me as I work as a developer in C#. So that's where I started. I think it's good to know about this, that this is a way to code, because when you go back to your daily work, I think it can actually be a benefit to you to know about that. And to go back to this readability question, there is a danger here, that if you put too much into this, it becomes totally unreadable. So you have to have some discipline and make sure you split it up into such steps. But when you're familiar with this function, you start to know what is the implementer trying to achieve by just looking at which functions it's using, because these captures the pattern of what it's trying to achieve. And then, of course, you want to have good names on the functions to understand where am I going with all this.